Greetings. If you are watching this series of lectures, you are probably a teacher. You're probably interested in learning about climate change and teaching climate change. Climate change is a very generic term. You probably already heard of it because it's being used interchangeably in the media versus global warming, climate change, environmental change, and so on. But we will see that scientifically speaking, climate changes on all sorts of time scales. In the current context, we are specifically referring to something called anthropogenic climate change or human-made climate change. To understand climate change, then, we'll go back and learn about what the basics of climate science are, what are the various reasons why climate changes, what are the different time scales at which climate changes, and if we want to understand how the future will evolve, what do we need to know about the past climate changes, and how do we know about past climate changes? What are the kinds of evidences we collect for the past climate changes? What are those time scales, and so on? And if we want to project into the future, how can we do that? We need to build numerical models called climate models, which we will discuss. And then in the end, we will have more focused attention on how climate has changed over the last 150 to 200 years since industrial revolution began, and where we are headed, and what are the kinds of things that have already happened in the time period since industrial revolution started. So already probably there is some confusion about what is weather, what is climate, and what do we mean when typically we say climatology. So just for clarity, we'll start by defining those things. So here we are showing a figure of temperatures, daily temperatures from Mumbai. So it is being shown for 1995 all the way through the summer of 2013. And you can see that there is ups and downs, which we call seasonal cycle, and there are wiggles in it, and there are peak temperatures over 30 degrees centigrade, almost 33 degrees centigrade. We know when that happens, March, April, May time period, and it cools down during the summer season and then kind of reaches a minimum in December when the winds begin to blow from the north. Right. So, we are taking daily temperatures which change as shown below here, and that is weather. So, if you are watching this video on, let us say, July 30th, you are used to thinking that July 30th, depending on where you are in India, typically rains and it is cooler than let us say May 30th. But it may just happen that there was some rain on May 30th which cooled the temperatures, and July 30th there was no rain and it got very hot. So, weather is kind of what you are used to getting on a day-to-day basis, but climate is what you expect. You expect May 30th to be warmer than July 30th over most parts of India, but on a given day it might just happen that May 30th may well be cooler than July 30th. So, climate is what we expect, weather is what we get. So, what is climatology? Typically when you ask somebody what is the climate of Pune, they might say it's mild temperature, not much rain, fog in the winter, and so on. So, it's a collection of quantities. When we say climatology in science, typically we talk about a particular variable, like what is the climatology of temperature over Pune or Mumbai. In this case, you will see this curve which is showing a whole year starting in January through December, and it's showing that the temperatures warm up through about to the end of May, and then the monsoon arrives, it begins to cool, the monsoon begins to go away in September, and then the temperatures warm, but by October, November, the winds change direction and they begin to blow from the northeast, so the temperatures begin to cool again. So, this is the climatological temperature of Mumbai. So, you can already imagine that climatology is defined as the average temperature over many years. Okay. What do you expect in the month of January based on 30 years of Januaries or 50 years of Januaries? So, it is just an average quantity over time. Climate and climatology are average over a certain length of time. What is climate change? For that, you have to first understand what is climate variability. What is climate variability? You can see that in this temperature being shown from 95 to 2013, the maximum temperatures and the minimum temperatures are not the same, for example. So, some year like here 2005 or so was much colder, 2007 was even colder than that, and some year here 1997 was warmer than most other years, and so on. These are the variations from year to year, which we call natural variability, because we will come back and see that they are not necessarily related to what human beings are doing. What is climate change then is if the temperature over this period that we are looking at is increasing or decreasing. So, for that let us look at temperatures over several cities in India: Chennai, Mumbai, Delhi and Bengaluru. Some records go as far back as 1882 and they extend to 2014. And you can see here that the long time series is smoothed a little bit, but it does not matter. You can see that the temperatures seem to have warmed. The minimum temperature here is about 22.9 degrees and here it is 24.7 degrees. And for Chennai, it has gone from 27.9 to 28.8. So, this we say there is a change. The mean temperature over an average, or even if you look for average temperature for January or February or any particular month, it has gone up over this period. So, that is a change. Does that mean that we have to always look for 100 years? Not necessarily. We will see that climate changes on many different time scales. The causes of those changes and the time scale at which they happen depend on what are the causes for the change, what are the drivers, what are the forcings. This is what climate change is about. So, to learn about climate change that is happening now and the global warming, we essentially need to understand what are the range of changes that are possible in our climate. For that, we literally have to go back to when the whole system came into being. The solar system is about 4.6 billion years old. Earth is about 4.6 billion years old. Since then, the continents have evolved, they have moved around, mountains have formed, mountains have disappeared, oceans have formed, oceans have changed in shape, depth, etc. So, all those things also affect climate, but more importantly, the sun himself has changed over time. The sun, we will not go into the details, has become more luminous over time, which means the energy coming from the sun has increased over time, which also changes climate. So, here is a record of some sort of a mean temperature of Earth as differentiated from the current mean. So, you take the current climate, you estimate the past climates and you look at how warm or how cold the past temperatures were compared to the current climate, and you plot them as anomalies. So, what I used a new term here, anomaly, you probably are already aware what it means. It basically means if you expect average January to be a certain way by the climate or climatology of that month, if it is above or below that long term mean, then you would call it an anomaly. So, the mean global temperature right now is, let us say, about 15 degrees centigrade. Any deviation from this value in the past would be called an anomaly. So, we are looking at temperatures going back to about 65 million years here, and you can see that the polar ocean equivalent temperature change going back to when the dinosaurs were just going extinct. The period was called Paleocene. So, you do not have to worry about these, but if you are a geology buff, then you know this is Paleocene, Eocene, Oligocene, Miocene, Pliocene, Pleistocene and so on. And you can see that the temperatures reached a very warm 12 degrees above the current climates in the polar ocean. Okay? Imagine how cold the poles are now. And they were that much warmer, 10 degrees warmer, which means there was no ice in the Arctic, there was no ice on Greenland, Siberia was not so cold, Antarctica had no ice, and so on. And there have been blips like this thing called PETM, which is the Paleocene-Eocene thermal maximum. We won't get into the details of it, but we will point to separate references or resources to understand those details. There is this warm temperature that persisted for a while, that's referred to as the Eocene optimum. And you can see that there is a cooling that went on for almost 30 million years. What are the causes for those? Okay, those are the things you need to understand why climate changed from such a warm state and cooled below almost to the current levels, and then it started warming again. So, at some point Antarctica started glaciating, which means glaciers began to grow on Antarctica. What would that have done to climate? How would that have affected the monsoon, for example? Okay. Then the temperatures got warm again during the end of Oligocene around 25 million years ago, and the Antarctic glacier began to thaw, which means it began to melt. The temperatures remained constant for a while, and then they have been cooling. But what you have to remember when we come back to this later on is that global warming is happening here at the end. So, we are in this long term cooling trend, and there are changes in the time scales at which temperatures are changing, and we are doing global warming at the end of this long cooling trend. So, we will learn about ice ages, why they come and go, and at what stage we are in, and at what stage we are heading to, and how we are changing that cycle because of what we are doing by the human activities and so on. So, there are various terms here that we will keep coming back to. This is called benthic delta O18, which basically means benthos means the bottom of the ocean, benthic means the bottom waters. Delta O18 is basically an isotope of oxygen. Oxygen you typically teach as having a mass of 16 protons, and it also has isotopes of 17 and 18, which means it has a couple of extra neutrons, and they are mixed together. So, depending on where the evaporation happens, where precipitation happens, where snow falls and so on, the amount of delta O16 versus O18 is different. So, in the past when we look at signatures of water at that time, looking at the differences in the O18 versus O16, we can infer the water temperature at the time and say something about how much ice there would have been. We will learn these details as we move along, but just remember that we use isotopes. So, I jumped a little bit to say that there are these kind of geochemical and biogeochemical evidences we use to reconstruct past climates. Okay, that is a lot of information, but each piece has additional resources that you can look up as we go along. Okay. So, let us focus a little bit on the more recent period of 500,000 years. So, this is time is going back here, even in the previous chart. I do not know if you noticed it. The time is going from 0, that is the present period here, 10 millions before, 20 millions before, and so on, to 65 million years before present. Here we are going back about 500,000 years, and then we are adding a little extra scale here of the last 100 years or so. So, we are showing now more detailed variations in carbon dioxide, methane, and temperatures over this period. Why are we doing this? Because we are slowly moving towards the main causes of climate change in the current period that we are interested in. So, in the last 500,000 years, you can see that the carbon dioxide in the atmosphere has changed by about 80 parts per million by volume at these time scales, but human activity has now increased it very rapidly beyond anything we have seen in this record. How did we get this record? We will see later on when we look at climate data that this comes from taking an ice core in Antarctica. Okay. So, there is a highly correlated variability in methane as well. Methane also, it turns out, can cause global warming. So, these gases that cause global warming, we call them greenhouse gases, as you may be already aware, and the temperature is changing pretty coherently with the greenhouse gases. So, the greenhouse gases have always been a part of change in climate, whether the climate change is driven by moving of the continents, changes in sun's energy or whatever. The effect on global mean temperature is almost always related to the changes in greenhouse gases associated with the driving forces. So, we will come back to how methane and CO2 are increasing, how the temperature is changing in response and so on. If you are paying attention, you probably also notice that there are slow changes happening on 100,000 year time scales, and then there is a sudden jump in CO2, methane and temperature, then there is a slow decrease, there is a sudden jump up, there is a slow decrease and so on. These are called abrupt climate changes. So, we will see why sometimes it varies slowly and sometimes it jumps up, and what does that mean for us. So, if we are changing climate, then we have to be sure that we are not creating a big jump all of a sudden. So, we will have to learn that. That is part of learning about climate change. So, that is kind of a broad overview of what climate is, what climatology means, what climate change means. There are changes happening on so many time scales. The causes and the drivers will be different, but first let us go back and try to understand what the basic climate science is. So, let us start by remembering that our earth is a sphere and it is tilted on its orbit around the sun, and it is rotating around its own axis, which means if you take a basketball for example or a volleyball and put a flashlight on it, you will see that the center of the ball will be more lit than at the top or the bottom because of the curvature. The same thing happens on earth when the sun's radiation is coming from far away. The rays are almost parallel, but the amount of area that is intersecting the energy is more in the tropics because of the shape of the sphere. The amount of energy being received for the same area is going to be less at higher latitudes, which means there is more energy being received per unit area, per meter squared, or whatever unit you want to use, compared to higher latitudes. Okay. So, then when you look at the amount of energy that is coming in and the energy that is going out, then you have to see, is there a place where there is excess energy coming in, and is there a place where there is energy actually being lost to space. Okay. That is what we will see. The net effect, of course, is we know that there are various processes being driven by the energy that we receive from the sun. All the energy is coming from the sun, right. There are some internal adjustments from volcanoes and so on we will look at, but the main source of energy for us is the solar energy that comes in. That energy is driving photosynthesis on land, in the oceans, it is creating climate, weather and so on. How does it do that? Essentially, then you have to understand how the energy balance happens. Think of sunlight as this fire. You can see it, right? At night there is no sun, you cannot see. During the day when the sun's energy is coming in, you can see it because that is mostly in the visible spectrum of light that we have evolved to see. Now, think of this pot as everything on earth. The sun's energy is coming in and heating this pot, and it's creating this kind of evaporation. You can see the steam here, and it's heating the pot. So, the pot does not look hot, but you know that if you put your hand on it, it is going to burn. So, the energy that is being reflected from this pot is essentially called black body radiation. So, that is energies in the so called long wave energy or infrared spectrum. So, the visible spectrum is the short wave energy. The short wave energy coming in is heating everything, and that energy is going back to space as long wave energy. And the energy balance is essentially how much energy is coming in as short wave, how much energy is trying to go out as long wave, and the climate change or global warming is essentially related to how that outgoing long wave energy is being trapped. That is what greenhouse gases do, or the changes in the so called albedo that we will come to in a minute. This is the basic energy balance. Short wave energy coming in, long wave energy going out. Okay. So, the earth itself has many components. It's a system. You can think of it as your body. You have the brain, the heart, the blood circulation system, the digestive system, the gland systems, skeletal system, nervous system, and so on. So Earth is functioning as a system. It has ice sheets, it has ocean, it has land, it has mantle and things that are moving inside that can create magma and emit it through volcanoes. There is carbon in the system. There are other greenhouse gases in the system. As things get heated, they warm up and evaporation happens. Water, it turns out to be one of the most important ingredients for moving energy, because when evaporation happens, that energy is being taken from the water body where evaporation is happening. It's condensing in the atmosphere, means that energy is being released in the atmosphere. So clouds can form, move somewhere and release the energy somewhere. Correct? That's what the system is doing. So we will see these points again and again and again. So you don't need to panic, and there are resources for each concept that are separately provided with reading material or additional videos and so on. So when we think about this Earth system, the climate, the energy balance and climate change, we have to see what is forcing the system other than shortwave radiation, what are the interactions between these components in the Earth system, and what are the feedbacks. We will learn the concept of feedback. This turns out to be very important, but let me explain it in a very simple way. Okay, so sun comes up in the morning, goes down in the evening. So there is a daily cycle of forcing by shortwave radiation or solar radiation, and sun moves back and forth. So there is a seasonal cycle. You have summer, winter, fall and spring. Not very strong seasonal cycle in the tropics, but if you go to higher latitudes, the seasonal cycle will be very strong. So even though the main forcing from the sun is just on the diurnal cycle or the daily time scale and the seasonal time scale, weather can change several times in a given day. You might have a bright sunny day in the morning, might get very cloudy by afternoon and rain in the evening and get cool by the night. So why can things change so much? This happens because each component of this so-called Earth system can interact with each other: the ocean, the land, the vegetation, the clouds, and so on and so forth. Okay? So the main causes for climate variability and change are shown here. They are called external forcing because they change the energy balance. If you look at the top of the atmosphere, look at the amount of short wave coming in, amount of long wave going out, that is the net energy balance. Anything that changes that net energy balance is called an external forcing. So changes in plate tectonics, when continents move, when mountains are built or destroyed, when ocean sizes change, it causes a forcing to climate, as we will see in the coming lectures. Changes in Earth's orbit, again we will come back to that. We know that Earth is tilted at a certain angle, the orbit is elliptical, and the Earth precesses like a top, and these change on certain time scales, and these changes in the orbit alter the distribution of shortwave radiation on the planet, which can kick off the feedbacks and create climate variability and change. And the changes in the sun's strength. As I said, when sun originated 4.6 billion years ago, it was not as luminous or as energetic as it is now. So over time, sun's strength has changed, but even on a short time scale, like a 11-year time scale, the number of so-called sunspots, where the magnetic lines on the sun are knotted up, can change the amount of energy that's coming out of the sun and reaching Earth. So changes, so-called solar variability, also acts as an external forcing. What is not shown here is human beings. Human beings have now become an external forcing. What does that mean? We are basically taking out carbon that is buried deep inside over many 100 million years, and we are suddenly burning it and releasing it into the atmosphere, and we are changing the radiative forcing. So we have also now become an external forcing. There are also volcanoes which change radiative forcing, as we will see, but these are the main ones shown here. The climate system, then, the atmosphere is being affected by the energy changes, vegetation response, more rain, less rain, very hot, plants can die and so on. Land can get hot, land can lose vegetation, ocean can take up heat, ocean can evaporate more ice can form or ice can dissolve. So, when ice changes, for example, that affects the energy that the atmosphere is receiving. So, there is a feedback. These arrows that are shown here are basically the feedbacks. Ocean and atmosphere are always communicating with each other. There is a strong feedback between them, as we will see, and similarly between land, atmosphere, vegetation, land and so on. So, you can see that the system is fairly complicated with feedbacks between all of them. This is why, even though solar forcing is changing on a daily time scale and a seasonal time scale, within a single day you can have many changes in the weather. Within a season you can have a drought, a flood and so on and so forth. Okay? So, the climate variations then are seen as changes in atmosphere, changes in ice, vegetation, ocean and land surface. So, we will essentially end up distinguishing so-called natural variability from anthropogenic variability. Any changes created by these changes, we call them as natural variations. And any changes we make by increasing greenhouse gases, by cutting forests, by building cities where we take out the vegetation and so on, we call it as anthropogenic or human-made climate change. Okay? So, it gets very complicated because human-made climate change can begin to affect natural climate change. So, when you have a change in temperature, let us say over Chennai, you will have to distinguish between what is a natural warming that may have happened over this period and how much of that warming is actually due to human beings. So, detecting the change is one thing. You can measure temperatures over 100 years and see that it has warmed, but then attributing that change to natural variability versus human made, not always easy, but there is a lot of research going on this, and so we call it detection and attribution. Attribution is separating the cause of human contribution to changes versus natural variability. So, again, those are details that we will keep coming back to again and again. The other reason why we get multiple time scales, we will see this again and again. The one temperature record I showed you showed annual cycle, the long 65 million year record showed multiple time scales, the 500,000 year record showed 100,000 year time scale and so on. Why are there these multiple time scales in the system? Again, in addition to the feedbacks, each component has a certain time scale of response which is directly related to its heat capacity. Okay? So, when we looked at that pot being heated on the fire, you know that as soon as the fire starts, the metal heats up fast because its heat capacity is very low, but the water takes longer time to heat up because its heat capacity is very high. Similarly, on earth, atmosphere, air has very low heat capacity, very low density. So, it heats up, responds in hours to weeks. So, on a daily time scale, you know it can heat up and cool down, and it can build up a heat wave over a few days and so on and so forth. Land surface also has a low heat capacity compared to the ocean. It takes hours to months. Ocean surface, on the other hand, is slower than both land and atmosphere, but it's somewhat faster than the deep ocean. We will see the differences as we go along. So, the ocean surface itself can respond in days to months. What does that mean? We will see that the ocean structure is such that the top of the ocean is light and usually warmer than the deep ocean. That's why it's on top. The deep dense water that's at the bottom can heat up slowly and can remain hot or cold for many hundreds of years. So, hundreds to 1500 year time scale. Glaciers 10 to 100 years, sea ice weeks to years, and ice sheets 100 to 10,000 years. So, these multiple time scales involved in the feedbacks that we looked at. So, it's possible that ice and atmosphere will feedback and ice will respond at a very different time scale than the atmosphere. Hence, you begin to generate many different time scales of change. So, let us zoom in quickly again to the long time scale and come back to shorter time scales. So, here is a hypothetical picture of changes in temperature shown just as a rough scale, but the order of magnitude is correct. If you go back from the present to 300 million years, you will see that the temperature compared to the present warmed to about 10 degrees of the current, and then sorry, you have to go from the back. So, we start here. 300 million years ago, we were close to the present climate. We warmed up to 10 degrees above the current temperatures, and we have come back to the current temperatures. So, you can see that there has been global warming in the past. What were the causes? Okay? That is something to remember. And the other thing to remember is this is about 100 million years ago, there were no human beings. So, when we think about current climate change and global warming, it is not just about what is causing it and what is the impacts, but also how it will affect us, because past changes may have been much bigger, but we were not around. So, it did not matter. If you zoom in to just 3 million years, you can see that there are many cycles of changes, and the amount of change has changed during this 3 million year period. So, there are smaller changes before, and now there are faster changes, and also the oscillation period is different. It is faster here and it is slower here. If you zoom into about the last 50,000 years, again you will see many oscillations. There is a warming that happened, and then we have remained here, and you can zoom into just the last millennium, last 1000 years, and you will see, we will come back to the details of each of these. So, you will see something called the medieval warming, the little ice age, the post industrial revolution warming, where the global warming is happening, and so on. So, essentially the points you should take from this is that climate change happens on very long time scales, on multiple time scales at any period you look at. The amplitude and the period of the oscillations change, but there is always change. So, when we say climate change, this is something we have to keep in mind. Let us take a look at a couple of possible amplifications of feedbacks. Okay? We said there are potential feedbacks in the system. What do they do? So, let us take an example of a climate response to some initial climate forcing. Let us say it is caused by changes in the amount of energy coming from the sun. Okay? So, the initial climate response happens to the change in incoming short wave radiation, the amount of outgoing long wave radiation changes, net energy balance changes, global mean temperature changes, and if the response is amplified by the climate system, then you can have what is called a positive feedback. Think of an example of a parent and a child. A child gets cranky and the parent shouts at the child, then the child gets even crankier, the parent gets angrier. So, this is kind of a positive feedback system, okay? Which means they can create amplifying responses. The best example you can think of is Venus compared to Earth. Venus has an average temperature of 460 degrees centigrade at the surface, whereas Earth has 15 degrees centigrade. If you look at the distance between the Sun and Venus, Sun and Mars, the energy coming in is not that different. But the feedbacks within Venus, where the so-called runaway warming happened, lots of positive feedback happened, and global warming got monumentally amplified and it reached 460 degrees, and Earth reached a balmy 15 degrees centigrade. You can now compare the other example of Mars, which you can do as homework. What happened on Mars? What is the temperature of Mars compared to Earth? Okay? There you had probably a negative feedback where some initial climate forcing change, again let us say from the Sun, created an initial climate change response, and somehow the system reduced the original response. So, you got into a negative feedback. This is like a thermostat. So, if you set an AC at a certain temperature, if temperature goes up, AC will kick in and cool the temperature, If the temperature gets too warm, AC will turn off and then the temperature will warm up. So, you have a stable system. So, any system that has positive feedbacks only can keep growing and become unstable. Any system that has a negative feedback can become stable. Why is this important? When we are perturbing the climate as human beings, we must watch to see whether we are kicking any positive feedbacks in the system. If so, what are the runaway responses that are possible? And we will see one very good example of that later on. Okay? So, just remember there are positive feedbacks in the system, there are negative feedbacks in the system, but all together do they form a net negative or a net positive? That is what we have to figure out. That is called climate sensitivity. How does the climate respond to perturbations? There is a more specific aspect of it where we look at how the climate responds to doubling of the carbon dioxide. We will come back to that, but remember these keywords: feedback, positive feedback, negative feedback, and climate sensitivity. So, let us go back to a little bit more about solar radiation and energy balance. Okay? So, we said that sun's energy in short wavelength is what is providing the energy. So, that is most of the energy coming to earth here in the visible ultraviolet. I think you know what happens to ultraviolet. It is getting absorbed in the stratosphere. If you do not know what stratosphere, we will come back to that, and there is a separate module for it. It is the upper level of the atmosphere where ultraviolet radiation is bombarding oxygen, splitting it and combining with another oxygen molecule to form ozone. Ozone is an endothermic reaction. So, ultraviolet is being removed by this ozone formation, which is very critical, because you probably also know that if UV comes to the surface, it will damage our skin, it will damage our DNA, and so on. There is infrared, which is the long wave. As we said, sun's energy heats everything. That energy is going back as a long wave. We ourselves are always emitting long wave energy, right? Our skin is hot. So, in the night we cannot see, but if somebody is wearing an infrared goggle, they can see us because we are emitting thermal radiation or infrared radiation. Sun's energy spectrum obviously goes all the way from gamma rays, X-rays, ultraviolet to microwaves and radio waves, but the energy that we are most worried about is this visible or shortwave radiation. How much energy is being trapped by Earth? This is critical, right? Again, you have to remember it's a sphere and it's rotating around its axis. So, if you go to the top of the atmosphere and look at the projection of the Earth that is intersecting the radiation that's coming in, it's a disk, right? So, if you, for example, take a basketball and shine light on one side, and if you look at the shadow, that will look like a circle, right? That's what is intersecting the incoming radiation. The amount of energy that is coming in at the top of the atmosphere is 1362 watts per meter squared now. Obviously, it changes over time because of sun's luminosity. But this energy is being spread over a sphere that is rotating, which means the area of the sphere 4 pi r squared is what is intersecting this energy and not just a flat disk. So, you have to divide that energy by 4. So, the average energy being intersected per unit area on Earth is 340 watts per meter squared. There is a separate module on how to do this calculation that you can look up if this is too fast. Okay? So, just remember approximately the numbers, or at least the concept that Earth is a sphere, it is rotating. So, it is basically intersecting the energy based on its surface area. What do we do with it? We basically want to balance energy over the Earth by looking at the energy coming in and the energy going out. So, if you take 340 watts per meter squared energy per unit area and you consider it as 100% of the energy coming in, clouds are reflecting like a mirror or scattering. That means it is not coming down, it is just being spread in different directions. That is about 26%, and clouds actually absorb about 23%. So, this reflectivity is called albedo. We will show in a minute what albedo is of various surfaces on Earth. 4% is reflected by the surface. It could be because of snow and ice or the high angle of water. So, if you look at the ocean from the airplane, if the sun's energy is coming at an angle, it looks very bright, there is a glint, but if sun's energy is coming in straight down, the ocean will look black. So, the reflectivity of the ocean depends on at what angle the sun's energy is coming in, and so on. Vegetation has a different reflectivity. Buildings and roads and cemented areas have a different reflectivity. So, all together there is about 4% of the short wave energy that is being reflected. So, there is a net albedo or reflectivity of the earth as a whole, that is 30%. So, only about 47% of the energy is essentially reaching the surface, heating everything, evaporating things, and so on. So, that energy has to be balanced by what is going back to space. Since 30% is lost by reflectivity, only 70% of the solar energy is reaching earth, which means 70% of that much energy has to go back out as long wave radiation if the system is to remain in balance, correct. So, you can see that the long wave radiation from the surface, about 5% of it goes directly back to space. The 29% of it is lost as latent and sensible heat, which means latent heat of evaporation. Sensible heat is basically because of the temperature difference between the surface and the atmosphere. So, that total is about 29%. But the main thing is to see that the numbers get larger than 70% internally. Okay, there is 109% here. That long wave energy that is absorbed in the clouds is reflected in every direction. So, some of it comes back, right. So, the greenhouse gases that are trapping the energy are putting that energy back to the surface, which is why we worry about greenhouse gases. They not only prevent the energy from going back to space, they reflect that energy back to the surface, which warms the surface, which is what we call global warming. Why do these numbers get larger than 100%? It's literally like taking a blanket and covering yourself. Your body temperature is 98.2 or whatever, but with the blanket you can trap your own outgoing long wave radiation and make yourself much warmer than your body. So, all these things that absorb outgoing long wave radiation create this warm blanket that makes the energy bounce around and become larger than what is received. But the most important thing is at the top of the atmosphere, the short wave and the long wave have to balance, and when we add greenhouse gases, this balance happens at a different temperature. This is what we call global warming. Okay. So, just to recap, we started by defining what is weather, what is climate, what is climatology. Climate is what we expect, weather is what we get. Climate variability is got some natural component to it, which we will come back to. Climate change happens on all sorts of time scales, which we will come back to. And there are many causes which cause climate change on multiple time scales, which we will come back to. But the main thing is it's always related to the energy balance, incoming short wave, outgoing long wave. So, what are the forces that change this balance? That's what we called external forcing. So, we will keep looking at these concepts over and over again and get into the details of the time scales, the forcings, the feedbacks, and eventually coming to human activities and what are the forcings they are causing, what are the feedbacks they are kicking into the system, and so on. See you next time.